What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
And welcome to another episode of the Concrete Logic Podcast. And today I have with me Concrete Bob Higgins, a fan favorite. No, Dr. Belkowitz is really jealous of Concrete Bob and all the views he gets on our YouTube. And actually, he has the most listened to podcast episode. I don't know if you remember it, Bob, or not, but you did one that we called The Importance of Properly Curing Concrete. And that one is constantly listened to. It's a great episode. So you look that up, check it out. But today, Bob's joining us, and he wants to talk about why or how people really don't understand how moisture moves through concrete and what alkalinity is and actually what it does inside concrete. So that's what we're going to spend our time on today. Did I get that right?
Yes.
Okay, good
Okay.
start. But before we get started, I just want to remind everyone that this podcast survives on your support, and I want to make sure you understand the ways you can help the podcast out. First is this: if you learn something from the episode today or any of the other episodes, to please share the podcast, get the word out. The second thing you can do is if you go to the podcast website, www.concretelogicpodcast.com. There's a donation button in the upper right-hand corner. You can click on that and you can give any amount. Any amount is greatly appreciated. And today I want to thank Frank Stankunas of Silverback Concrete. He donated recently. Frank, thank you for your support. So if you would like to hear your name on an episode, we can do that if you donate to the show. Also, while you're there on the website, there's a little microphone in the bottom right-hand corner. If you guys listen to our Dan Baker episode, that episode was centered around a voicemail someone left me. Go back and listen to that. So you can do that as well. So you click on the microphone and say, hey, I want to hear from Concrete Bob, or I want to hear about a certain topic. You can leave me a voicemail. And then lastly, real quick, if you like the format that we have, the podcast format, you like listening to these episodes, and you are an engineer that needs professional development hours, you want to check out concretelogicacademy.com, and you can get your CEUs or your PDHs, whatever, on the academy, and basically listen to an episode. You complete a quiz. It's questions, making sure you understand the topic that we discuss, and then there you go. You got your professional development hours. We track that all for you on the academy. So, with that, Concrete Bob, let's get back to the topic at hand. We're going to talk about how moisture moves through the concrete and what alkalinity is and what it does inside concrete.
Thank you. What people don't understand with moisture when you're dealing with the building sciences, for example, is moisture exists in 5 different forms that can affect buildings. We're not going to deal with the 5th one because it's it's kind of like a side chain because it's dealing with frozen water. That's a regional issue that I would talk to somebody in that area specifically about that. But we're going to cover the other 4 forms of moisture. Now, the three forms of moisture that we're familiar with in atmospheric conditions, again, is gas, liquid, and a solid. So we're going to ignore the solid for this. What we are going to concentrate, though, on is the water vapor and the liquid. Now, the water vapor and the liquid, I've been looking at all these studies globally, and there's so many exceptions to how moisture moves and what's causing moisture problems that the narrative that we've been getting for so long that's been assumed to be correct and factual isn't neither. Because if you look at suspended decks and you look at some of these other multi-story buildings, you can often have higher moisture levels on the elevated floors than you do with slab on grade. And there was a study done back in 2015 by the Florida Solar Commission where they were trying to look to see if flooring materials such as carpet would affect the insulative properties and help reduce cooling and heating costs. And what they found out is the center portion of the concrete tends to be adiabatic. Now, adiabatic means it's not changing temperature. And if it doesn't change temperature, the water generally doesn't move. And that's what they found out. Then I looked at our earlier study in 1974 by the Army Corps of Engineers where they were evaluating concrete for nuclear vaults. And during the 500 some odd days that was studied, the center portion of the concrete, the moisture levels never changed. Well, it should be drying out or should be going in. But one of the things that they did find is some of the models where it was cooler on the inside portion of the concrete, it actually got what they called supersaturated. Well, that goes completely in conflict with what we've been taught, how moisture moves from the bottom of the slab where it's nice and cool to the top surface slab where it's generally warmer. Well, that doesn't happen. Water moves from warm to cool, period. Now, when you have other types of moisture movement, that is a chemical reaction of sorts. And that's why we got to talk about how the different types of moisture move, because now you have adsorbed moisture and absorbed moisture. That occurs in concrete constantly. Those do not respond in the same way that an open, unfettered condition is. So when water vapor, when it evaporates, it goes from a liquid to a gas. Well, for whatever reason, the concrete industry and the flooring industry got convinced that measuring the gas is a good way to measure concrete moisture content. That is ridiculous.
Talking about the RH.
Yeah, that's ridiculous. I love the RH probe. If they would move that to a 1-inch and 2-inch depth, that would be one of the best analytical tools we could get. But as it sits right now, it's actually misused. And I've fought it long enough to now know that it's intentionally misused because it keeps people busy.
Well, that goes with a lot of things in the world, but I don't want to get us off.
Yeah, I know.
Topic.
But I'm concerned with people that get thrown under the bus.
Yeah.
There's too many. They get thrown under the bus with the RH. Well, it's 90%, so it's over 90%. Well, none of the probes evaluated in the 2170 are accurate above 90%, but they're constantly giving these figures above 90%. That is false information because it's not repeatable. That is not a characteristic that's within the parameters of the sensors. The manufacturers of the sensors say it's accurate only up to 90%. So why are they doing this? It doesn't make any sense. So there's manufacturers basing their warranties on basically fabricated information.
Well, do you think that, I don't know, how long has the RH probe been around?
It's been around a long time.
Yeah.
And it's been used for decades. And the problem is most of the evaluations have been just on the mixed water. I have not seen any supporting data for concrete that's been in service. All the data I've seen, like the Head&Blood study and the CTL study, they were based on new concrete and the drying rate of the concrete as the mixed water evaporates and is consumed by the cement gel. And I even saw the probe where they put the probe in, and they're showing the top surface of the concrete during this initial drying rate. It showed that the relative humidity of the top inch of the concrete dropped to 74%. Well, there's no cement formation. Cement formation, even at 80% when it does start, is only about 10% efficiency. It should be around 85 to 90%. But they're targeting a lower number for God knows what reason. I think I understand why they did that, because it was just a misinterpretation of data. But they're actually preferring the concrete be defective. Because if it stays at 74% relative humidity before you put it on a floor, that is not recoverable. And that has been verified by Texas Transportation Institute, where they actually water cured concrete for 7 days in a lab, but the top 1 inch of the concrete was a full 20% lower in compressive value. Now, again, there's a compression strength test that we use, just evaluates the concrete in its entirety. It's based on breaking. It's not based on any squashing or possible crushing. It's only based on the break. So that lower portion of cement formation has been completely ignored. Now, there were other studies done. There was a composite, and I've done this in several presentations I made, where the concrete industry showed the effect of temperature. Now, the effect of temperature, for example, if it gets to 90 degrees, the development of strength of the concrete a year down the road, it doesn't hit its marks. Well, what was really amazing about that, they took those samples at the 90 degree and then higher, it gets worse and worse as it gets hotter. They took those samples for the remainder of the 365 days. They put them in a chamber, environmental chamber, of 73 degrees, 100% relative humidity, and they still couldn't get the full strength back. That damage was irreversible. And that's what we're seeing in the field. Now, the data that we have for the field is based on type 1 cement. Type 1 cement is a very specific reaction. It develops more heat than type 2, and there's other differences. And then when they went to type 1-2 combination in around 2005, it wasn't reevaluated. They didn't note any of the changes that would occur, even though they recognized it reduces the initial heat of hydration. But it also changes other things that they just ignored based strictly on the 28-day break. That's the big evaluation. That's the only thing they evaluated. Not the long-term durability or the effectiveness of water cure or anything else of that matter. And then between 2002 and 2018, they started adding cement kiln dust, which is another change, which makes the concrete more alkaline. Now, this becomes regional because wherever you take your raw materials from, this is going to have a different composition than another area of the country. So you can have differences in alkalinity from area to area. So we can't use a uniform evaluation there either. But that's been ignored.
Yeah, we got to define what alkalinity is.
Yeah.
What is
alkalinity is basically a concentration. Now, pH is a way they evaluate it, but that's only tells you there's something there. It doesn't tell you how much there is. So one of the curves I use, once you get to around 10%, if you do a pH test on a 10% solution versus 50% solution, it's pretty flat. It's right around 13, and it can finally get to 14. The difference between 10% solution and 30% solution can be the difference between a desiccated surface or a non-desiccated surface, or a ruined floor versus a floor that's fully functional. And none of that is being evaluated. They're just, oh, well, somebody must have done something wrong. Yeah, they're given the wrong parameters. Basically, every ASTM standard at this point is now out of date. We don't have any accurate ASTM standards any longer for evaluating moisture tests or some of these other properties of concrete, because it's still based on the pre-2005 combination where they added the 1-2. It was type 1 cement back then. That was a primary use. Now, people will try to tell you that it's not that big of a deal that we change these things. And I just give type 1 and type 3 cement as an example. Type 1 and type 3 cement are completely different, and they're evaluated different. They're even given different categories. Because otherwise, why not just call it type 3, type 1? And they said, well, they're different cements. I said, the only difference in those cements is the grind size. A finer grind is the type 3. But chemically speaking, type 1 and type 3 cement are exactly the same. They're chemically exactly the same. But the type 3, because it's a finer grind, it develops heat much quicker, and it develops strength much quicker. So that's a rapid setting cement, rapid strength gain. But again, it's no different. But then they add the type 2 to give it more sulfate resistance and to slow down the heat of hydration. But once you change something, you've changed everything. And they have not recognized what those changes are because they keep evaluating strictly on a compressive strength value. Now we get them.
Well, let's hold on. I mean, so we have different ASTMs, right? So we have ASTM C150, which is for type 1, type 2, type 3, type 5 cement. Then we have the ASTM C595, which is for blended cement. So when you say these are no longer, I guess, useful, what do you mean by that? Because if we have a different ASTM for blended cement, which that's what type 1L should be in, right?
It should be, yeah. But I have not seen any data on it. I've asked for data, and nobody seems to have it, and that's disturbing to me. You think that before they start using this to substitute type 1, type 2 cement, they would have a lot of data on it. And okay, this is what it does. This is the durability, and everything else. Now, when it first came out, I had a debate with one of the cement producers, and they were telling me that it was a 1-for-1. Basically, you do everything exactly the same as you do with type 1, type 2 cement. And that's what they're promoting. And that was heavily promoted on LinkedIn and some of these other things. And I took issue with it. Well, turns out that it's not a 1-for-1. All of a sudden, these seminars start coming up, and they're actually doing revisionist history, because now here's the differences you have to incorporate when you're dealing with type 1L versus type 1-2 cement.
Yeah. Well,
That's
yeah, I think they're recognizing that they screwed up there, and I think the 1-for-1 was, again, this is just me speaking for myself, but I think the 1-for-1 was based on, hey, we want to be able to sell you the same equivalent amount of cement to do the job that type 1-2 was doing. So you get this, yeah, for one, and that's why they did that. But they have gone back, and like the state of art report that talked about type 1L cement, and blended cements, they revised that and then admitted that there are issues with type 1L cement, and they started listing those things that came up. So I think that was that 2010, 2011, that first paper came out, and then 2024 was the latest one. So it's going to, continually to evolve. But I want to, that's a whole different episode that we could handle, Bob, but I want us to keep on, stay on track here. So
but that's
alkalinity and yeah, no, I think we all recognize that. And I think what's great about this, I think, Bob, is that now that this material change, I think now that everybody's paying attention. Like you've mentioned in the past, they've made these changes, and I don't think people were paying attention. They just kept moving along. And now that we've made this change to type 1L cement, I think the good thing out of this is now it's like, okay, I use concrete. I need to understand what the hell concrete chemistry is and what it does, because you can't, like you've been on this episode or this podcast numerous times and we've beat it over people's heads. You just like, you gotta, this concrete, you gotta treat it, the cement, I'm sorry, is different. And when it's in your concrete, you gotta change your method. So it's got different handling methods, it's got different curing methods. You just can't do what you did before, because if you do what you did before, you're going to be disappointed with the results because you're not going to get what you got before. So
Yeah.
I think that the good thing about all this is that, hey, you got to pay attention.
Yeah. And see, that should have been known before they even started. That's a fundamental issue. And that's where my problem with the presentations lies. We have these changes and they only address it after the fact. Why? Didn't you know this before? So either you didn't know, shame on you, or you did know, and even more shame on you. Now, alkalinity now complicates this even more, because alkalinity tends to prevent moisture from contacting the clinker. Because what it does, it tends to, as it concentrates and there's more water demanding materials such as limestone, it takes a lot of water to the entire concrete mix. And they're trying to go to lower water cement ratio, trying to correct that by putting plasticizers and these other materials in there. But what happens, they're showing time and time again, the concrete surface is self-desiccating. Once it self-desiccates, you can't fix that. You've got permanent damage, which is why I brought that study up where they cured the concrete in elevated temperatures, because elevated temperatures, well, that's the reason why it's doing that, sort of. Because the calcium hydroxide, that's a spinoff, also becomes insoluble as it gets warmer. There's all these parts of the puzzle that are not being addressed. So as these parts of the puzzle are not being addressed, that's why these studies from the 90s and from 2 weeks ago, they read the same thing, all come to the same conclusions, but it's not fixing anything. We have this technical hamster wheel that we're dealing with. So the real monkey wrench in all this is alkalinity. Now, alkalinity, specifically the sodium hydroxide. Sodium hydroxide, as it concentrates, suppresses the solubility of calcium hydroxide in a similar manner as elevated temperatures. But now this will do this in cooler temperatures, because calcium hydroxide gets more soluble as it gets colder, and sodium hydroxide gets more soluble as it gets warmer. So when we get in these medium ranges and you start getting solar radiation and other influences for a warm building, you're now damaging the surface. But we have this false sense of security. Well, if we cure it, we'll get cement formation. No, that's not happening, because they were showing, even with curing compounds and a 7-day water cure, they're still losing about 20% of the value in lab study. And that's a carefully controlled environment of temperature and humidity. They're still losing 20% in lab study. Can you imagine how much worse that is in the field? And those samples that were kept in an environmental chamber for the remainder of the 365 days, we don't have that luxury in the field. It is so much worse in the field that we're not taking the field studies and bringing them into the lab. We're bringing the lab studies and putting them in the field, and then wondering what the hell happened. Well, that is an isothermal condition. Isothermal condition means you've controlled the amount of influences. But once you've taken the field in a non-isothermal condition, you can look at almost any study of any kind of test, concrete or whatever, it doesn't matter. Once you go from isothermal to non-isothermal, very rarely do those results match. And we're ignoring that. I don't know why the tail is wagging the dog here. So with alkalinity, it also increases the viscosity of water. It suppresses the evaporation, it lowers the RH, and it makes the water thicker. It can actually turn it to almost a syrup-like consistency. Well, you can't draw that out. We have these issues that are going on in real time globally, and we're still not addressing it as these studies keep recycling and doing the same thing over and over again. Well, That's the definition of insanity. It's doing the same thing over and over and expecting a different result. We need to deal with the realistic conditions that we have now. 1L cement can't be evaluated in the same way as type 1 cement, but we're still doing that because you take all the ASTM standards that are based on type 1 cement and stick them over here with the blended cements and everything else. That's fine, but each blended cement has its own set of characteristics. Those need to be evaluated separately. We're not doing that. Instead, they throw this out there to the concrete contractor, and then they end up getting thrown under the bus because the concrete goes bad. Now that I'm on it, why do they put vapor barriers underneath the concrete? Why do they do that? There was a misinterpretation of moisture movement in concrete. Concrete actually doesn't allow free moisture movement for a long, long time. And what happens by the time it does allow movement, usually the vapor barriers are already deteriorated to the point where they're of no use. So what are we doing? Now, I do like vapor barriers if there's contaminated materials in the concrete, or you're dealing with radon gas or something like that, but you need a high quality one, because anytime you get a crack, you get a through crack, you're going to have an avenue of migration. But through the concrete itself, concrete's kind of like a loaf of bread. If you bake a loaf of bread, the crust and the sides and the bottom are different than the center of the bread.
Right.
Still bread, but the composition's different. The composition around the gradient portion of the concrete is all different. That's where the moisture is moving around. It's going in and out and down and through and coming up and coming in from the side. It's not doing this.
Well, does the vapor barrier prevent salts from being drawn out of the soil into the concrete? Is that a possibility or no?
Yes, but what happens is by the time they're effective, they've worn out. I've heard that there's durable ones, and I'm not going to contest that, but the ones I've seen when we've done core tests, once it's past about 10 years, I've got a really good one I have from Bob Blockinger, where they did a core test, and there's almost nothing left of the vapor barrier because they're not using virgin plastics, for example. They're using recycled plastics with some of these, and they just say, well, we have a millage requirement. It was got to be this millage. Well, it also should have a quality control standard as well, because if the salts in the soil attack the vapor barrier and it breaks down, not doing anything.
Yeah.
So we keep doing, again, it's a hamster wheel. If you're going to put a vapor barrier under there, put one under there that's going to last 30 years. Let the concrete get really, really dense and leave it uninterrupted. But the other dumb thing they did is they put the vapor barrier underneath the concrete. They changed that because of that misinterpretation of moisture movement through the concrete. Now, all the data I saw prior to that, and it's this 1998 article in the Concrete Bulletin for ICRI, showing how concrete will curl if you put the vapor barrier directly underneath it. Well, that's what's happening. So now the concrete industry has shifted where ASCC and ACI both recommend you do your flatness test within 72 hours, and preferably before you cut your control joints. That's because the concrete's going to crack, warp, and curl. Why? Because the vapor barrier is directly underneath it. It's only one way for the water to leave the concrete. Well, we can't have that because if it gets rained on, the water will come through the concrete. I've been told that. I said, show me where that's happened. And all the information I have read is anecdotal. I've not seen any empirical data on this. Now, I've been asking this now for well over 20 years in some areas and 30 years in others. Show me the empirical data. You say this is well established and well studied and is accepted as fact, then you should have a lot of data. How come I can't find any? I mean, I've been in this business. I'm closing in on 50 years, and I haven't seen any data on this.
It's just become the standard design.
So your companies like Baker Concrete are being asked to place this concrete, and you're doing so with blindfolds on because you don't know what's going on in that concrete. So you do the best you can, And if something goes wrong, the first line of blame is the concrete contractor. I know.
I was looking up the ASTM for vapor barrier. Are you familiar with that?
Yes. Haven't
ASTM
looked in a long time.
yeah, E1745. Does that sound right?
I believe so. I haven't looked at that in a long time.
Yeah. Huh.
Now,
Interesting.
when they say, well, vapor barrier is effective, it stops moisture from moving. Okay. Explain this then. One of the projects I was involved with a while back in 2014, they were going to use moisture mitigation for this project. It was 3 stories, and it was going to add nearly $1 million to the cost of the project. It was going to delay the project between 3 and 4 months. So I looked at the data they sent me, and the 3rd floor had the highest average moisture content, 2nd floor a little lower, and the ground floor the lowest. So, well, if it's coming from the soil, how do you explain this? And the inspector on the job site couldn't. I said, this is called the stack effect. Warm air rises because it's a non-acclimated environment, so you have the stack effect. I said, this is moisture not coming from underneath. This is moisture coming from the surface. And that most moisture issues come from the surface, from the ambient conditions, not from underneath. Because that's what you have, that permeable layer. Well, the permeable layer, it's absorbing a lot of moisture. And you look at these cross sections of concrete that I showed repeatedly in these presentations, it's so much different. But then they drill the hole down past where it's damaged and say, well, okay, here's the relative humidity. That has nothing to do with the damaged area. The damaged area is porous and permeable and it's full of alkaline salts. It has a tendency to collect there. That's where I gave over 30 years ago, I made a hypothesis that about early ASR, and I was ridiculed for it. Because I said, no, that's time dependent. I said, no, when you're first curing concrete, your lighter aggregate, the amorphous aggregate, tends to float to the surface. And then with the concentrations of alkaline salts, as you're trying to cure the concrete, it'll start reacting. And 2 years after I made that theory, all of a sudden this article comes out talking about near surface ASR. And then now more and more people started studying it. And that happens. Well, again, that's a misinterpretation of the data. So I'll get back to the 3rd floor. So I said, this is coming from the surface. So you got a damaged surface. The damaged surface is absorbing the moisture. So, well, how do we fix it? I said, we'll stick fans on it. And what we'll do is we'll moisture test it. And once it drops below 4.5% with a concrete moisture meter, go ahead and start, but keep the air movement because you don't want dead air. Dead air is deadly. I tell people that dead air is deadly. Don't, keep the air movement, because what happens when water evaporates, right at the point of evaporation, that you get what's called evaporative cooling effect, and the moisture wants to resist leaving the surface. It starts to cling as it gets colder. So by moving air across it, you basically are scrubbing it. Now, it really helps if you can add heat, but that's not always available. So we started blowing air across it, and in about an hour or so, the moisture levels dropped to right around 4.5%, a little bit lower. I said, well, go ahead and start installing the floor, but follow the air. So they were blowing this across and did this for all 3 floors. They lost less than 2 days of progress, and the floor is still down. Here's 11 years later, and the floor is still down. And they said, oh, no, it's moisture coming from underneath. No, it's not. Very rarely does that ever happen. Does it happen? Sure. But it's pretty rare. We need to reset. We need to go, okay, let's go back, stop assuming and stop accepting these myths that we've been taught as being factual. We need to question everything. Because if we do, what happens, I spoke in this gentleman, Larry Marble, he worked for Tarkett for a long time. His last 3 years with Tarkett, with the group of installers he went 3 years with this group of installers with no moisture claims. Well, they couldn't explain that. Moisture equilibrates in the concrete. So when you put a floor down, relative humidity goes back up. And so there are over 104, there's 148 million plus homes in the United States. Over 70 million of them are built over slab on grade, but only several thousand have failed. There is no correlation whatsoever with the equilibrium of the water vapor and the floor failure. It can't be because it's too low. If you take a unit of water vapor, you take 1,700 units of water vapor will make 1 unit of liquid water. That's how we evaluated steam explosions in fire science. That's why a cup of water, if you drop it in, it immediately will expand to 1,700 volume units of water vapor, and that's a damn dangerous explosion. That's why steam explosions are so dangerous. You drop water in there, bang, especially where they're melting metals and that type of thing, because then it is an instantaneous reaction. And that's what you're looking at. So another head and blood study that they did where they were evaluating the capillary water said that's much more accurate than relative humidity. So they took a sample of concrete, put it in an environmental chamber, 100% relative humidity. So there's just humidity, no liquid water that they could see. They put it in a gravimetric oven, and it was such a low difference they couldn't calculate how much water was in there. But that's your 1,700 to 1. Again, and then if you change temperature within the allowable ASTM standard, which allows 65 to 85% relative humidity, if you measure a dry concrete at 70% at 80 degrees, it becomes 100% relative humidity at 70 degrees. So 80 degrees down, let's say 65 degrees, goes to 100% relative humidity. So is there more moisture there? No, there's no more moisture. And if you look at volume, none of that makes any sense. So why are they using this? Because if you take a cubic meter of space and you want to fill it up with water, it takes a little over 264 gallons of water to fill it. It takes less than 2 ounces of water to get to 100% relative humidity. And they're trying to convince us that's what's causing these flooring failures.
Mm-hmm.
So we have all this garbage information we keep getting fed, and we're not correcting anything. But the ones that are given the proper information, we're ending these claims. So if we start addressing the type 1L cement and evaluating it on its own merit and making the adjustments, which should have been done on the front end, rather than thrown out to the industry and say, oh, okay, well, now we have to do this, now we have to do that. That should have been known. Why wasn't it known? Who's responsible for that? That's what angers me, because I've gotten into litigation avoidance. I want to keep people out of court. I want to keep the damage down to a minimum. That's my whole effort now when I'm dealing with these problem jobs, is eliminating the problems, because it's ridiculous. Because ever since they changed the requirements for moisture testing, the claims have tripled. And they said, well, not everybody's testing anymore. Well, not everybody's testing because the testing doesn't work.
Right.
And still have a failure. They don't test, they might have a failure. But there's no statistical support for what they're doing. Everybody does it because they've been told that's what they need to do.
Yeah. All right. Well, I think, so just to sum up today's discussion, water and concrete is not one thing, right? There's liquid water and water vapor. They behave differently. Correct? Got that right so far? And then the moisture movement through concrete, it carries the chemistry with it. So when water, moisture moves through the slab, the alkalinity moves with it. So, and that's what gathers at the surface.
Yeah, and that's diffusion. Then what happens is it becomes chemically active, and then it becomes more and more, increases in its attraction of moisture into the salt. Because what people confuse, they've confused basically diffusion with moisture migration. It was totally different. And with absorbed moisture, you have these hygroscopic, hydrophilic elements in the concrete where the water will travel and it can actually defy what it normally would do. That's why you see if you take glass and put it in water and you watch the capillary rise in glass, it shouldn't do that. And it won't do that in an open system. There's a single influence right there that changes the properties. So
Yep.
we're not looking at them because they keep taking these singular line items and applying that as, okay, well, this is what it does. Well, what happens when you add this? What happens if you add this? That's why non-isothermic conditions are so important. We need to start evaluating concrete outdoors where it actually is placed, like cold weather, warm weather, hot weather. Those should be dictating what's going on in the lab, not the other way around. But I don't know why laboratory studies have taken precedent over what's going on in the field. And I'm baffled by that.
Yeah. All right. Well, let's pause on that today, and then we'll pick that ball up and argue that for another day. How's that?
Yeah. Okay.
All right. All right, Bob. I appreciate you coming on the show today, and always enjoy our discussions on concrete chemistry. So thank you. And folks,
Thanks for having me.
thank you. And folks, until next time, let's keep it concrete.